Okay, I think we can go ahead and start the next session. Welcome back. So it's my pleasure to introduce the next speaker, which is Berkeley's very own Professor Dan Stamper-Kum. Dan's a AMO experimentalist, and he's a professor in the physics department here, in addition to affiliations with LBL, et cetera. And Dan has taken on the sort of Herculean task of directing the NSF QLCI Center here at Berkeley, the Challenge Institute for Quantum Computation, and today he'll be telling us about all the great work going on and that is planned for the renewal.
All right, great. Thanks everybody for coming. I was aware that maybe I got my talk title and abstract in kind of late, so some people didn't even know the title of my talk. And this title is about as useless as, it's about the same as having no title. I apologize. It was whatever, 10 minutes, whatever, before midnight I sent it in. Anyhow, what I want to do with the time is just share with you what our plans are for the CIQC, the Challenge Institute for Quantum Computation, in the coming, 6 years, and in particular with our guests from elsewhere, from industry, from the national labs. I mean, just to hear kind of what we're up to, because I would love to hear from you all whether what we're doing is useful and how we can connect with what's happening in the quantum industry and in national labs and be most productive partners with you. So this is a great occasion for quantum computing. First of all, quantum is celebrating a very big birthday. Here's quantum, the original Herculean quantum. But no, so not his birthday, but it's apparently the 100th anniversary of quantum mechanics. Actually, by my accounting, it's the 101st birthday of quantum mechanics, given that the term quantum mechanics appeared for the first time in the literature in 1924, I believe. That's interesting, because if quantum, the person and the subject, is 100 years old, why do we still teach it, for example, as a modern physics topic? So here at Berkeley, when we teach the physics series, there's the last of 3 semesters called whatever modern physics, and that's where quantum mechanics is, which is 101 years old. And it's kind of odd that it's inside of these textbooks. Nevertheless, people are hyping up this year being a big anniversary for quantum, not just that, it's a nice accomplishment in physics, but also really inspired by this thought that quantum entanglement in an engineered control way is going to produce a lot of new capabilities scientifically and technologically. That's really the big deal. Okay, so this inspired, as you know, the launch of the National Quantum Initiative back in 2018. And as part of that National Quantum Initiative, there were supposed to be a bunch of national quantum centers, half of them supported by the National Science Foundation. So that's when this Quantum Leap Challenge Institute was initiated. Initially as a 5-year program, it then became like a 6-year program. And thank goodness, as of a few weeks ago, we submitted our full renewal proposal. Now it's sitting in the hands of some reviewers, maybe some of you. And hopefully we'll move on to the next stage. And it bears asking whether the NQI has been a success. I mean, people went to the halls of Congress and said, hey, we need to lead. What did I hear the quote recently? Whoever owns quantum owns the future. That's something I heard people say. That's just painful. But anyhow, that's the truth. And so do we own quantum? And I mean, to be honest, I think the most stupendous, most science fiction kind of advances in quantum computing have actually happened in the hands, I believe, of the quantum industry. And the efforts in superconducting quantum computing, ion trap quantum computing, and now also neutral atom quantum computing are generating physical systems that are just astounding, that we have at our disposal, as a future quantum computing technology, but also as a physicist, this amazing box with all these knobs that just displays quantum mechanics at an extremely exciting level. The whole advent of logical qubits and error-corrected matter is just super exciting. So in light of all this, what role does an academic center like the CIQC, the Challenge Institute for Quantum Computation, what kind of role does it play? And I feel like I've gotten answers to the role we should play through events like this. So last year, I moderated a panel after having a bunch of great speakers come to this Quantum Industry Day, and we sat around right here on the stage, and I asked just point blank, like, are we doing the right thing? Here we are in academia. We think we're serving this role, but what do you say? And the feedback we got was actually, maybe just because, you know, it was hosted here at Berkeley, people were naturally kind. But they said, yeah, you're doing the right thing. You know, like in industry, we have roadmaps to follow. We need to really charge down that road. We're going to do so very efficiently. And what we need is a bunch of people in the back kind of doing this guided diffusion to find out what else there is, to find alternate pathways on this road that we're following, to figure out the dark horse that we should all be riding, to look ahead and see where the roadblocks are that we might stumble on. So that's kind of the attitude that we're trying to adopt in terms of what we should do as a center. And another event that also happened here right at this stage, also me sitting around on a panel, was sitting around with a bunch of people from other industries, not just quantum computing, but you know the future customers of quantum computing were here in the hall and wanting to learn more about quantum computing. And what I was trying to emphasize to them was that they should be careful believing what they read in the newspaper and in business journals. There's just so much garbage and hype out there, and a lot of progress in science is being announced through press release instead of through peer-reviewed publications. So another role we think we ought to play is to try to bring people in for more of a scientific discussion about progress, so that we can more comfortably rely on where things are really making progress. So that kind of guides the way we try to establish the CIQC's activities and research portfolio. So, you know, obviously we should be looking at both fundamental research, so the things that really start new things, but also, you know, really looking at problems and trying to refine them, so advanced research on certain techniques. We should keep paying attention to the possibility of like disruptive technologies. Maybe the way everybody is approaching quantum computing is not the way quantum computing will eventually work. So we're probably in a position to find those disruptive technologies if they're still out there. We should keep at it. Good luck to everybody. I hope there is no quantum winter, but if there is, we are your parka, and so forth. So now I'll tell you about the CIQC, some of the directions we're taking. I'm a little afraid it's going to be like slide karaoke, but hopefully there'll be a little bit of sense in the presentation to give you an idea of what we're working on. And again, what I'd love is for the discussion afterwards and in the halls and at dinner, whatever, to be like connecting with us to let us know if we're going in the right direction, where we can work on things together. So the CIQC is trying to maintain a kind of broad perspective on quantum information science, that we should, as I stated, work on kind of the fundamental aspects, not just of science, but also quantum engineering, how we're going to make large-scale systems operate. And the CIQC kind of relies on, or divides itself into, I would organize it as like 5 core areas of expertise. The CIQC has a significant presence in, on the experimental end in 3 of the quantum computing platforms. So we have a lot of people who have expertise in neutral atom quantum information science, solid state, including superconducting circuits, but also some of the quantum optical approaches that rely on solid state, and then also expertise in trapped ion quantum information science. We have a large theoretical quantum information theory group, but this is actually a hodgepodge of really a lot of people from theoretical computer science, quantum physics, mathematics, and chemistry. And 2 very strong connections made through the CIQC are to connect strongly, as here, with the Simons Institute, sort of to help maintain the quantum pod and events like this that are going on. Also the Institute for Pure and Applied Mathematics down at UCLA. And our idea here is that, you know, there's only, I don't know, 10-ish or so people on that list, but we'd like 1,000 people to work on the problems that are really of interest. So if we can, bring people in and get the conversation going, we don't care if the next big breakthrough really comes out of the CIQC per se. We want the next breakthrough to come out. So we'd like to engage with a lot of people to make that happen. And then we also have a group of people that are more in the sort of quantum computer engineering side, thinking about this sort of question of a stack and how to connect the highfalutin ideas about algorithms down to the hardware level. The research kind of long term, I would say the CIQC is directing itself at 3 large research challenges. One is not just realizing the power of the quantum computer, but also discovering it. Like, I'm still concerned that we don't really know what quantum computers are going to be good for. We know of a couple of examples of really established quantum advantage, but not everything. So I keep having this idea that there's like a tip of an iceberg, and we know the tip, and we think the iceberg exists. So I feel like we should invest a lot of energy in figuring out what's the full girth of that iceberg. We do work on experimental and kind of engineering work to build new technologies and then also find their applications not just for quantum computing, but for other applications as well. And then the last thing, being here at a university and thinking a lot about science, and also in the style of the Simons Institute, thinking how does quantum information science and the ideas of quantum computing allow us to understand nature better? In terms of the specifics that we're covering in the next 6 years, here's kind of the research lineup. So on the first topic, I guess our focus is on quantum advantage. So we have some work on verifiable quantum advantage tests. I'll say a little bit about some of these topics as well. In the area of engineering quantum technologies, we think we're at the verge of being able to play with various scalable architectures for quantum computing, like in this near fault-tolerant quantum computing era. Boy, NISQ went away really fast. But also look far ahead and see whether there's roadblocks in terms of fidelity, speed, and scaling of the technologies that people are pursuing. And then we have some ideas also on the science that can come out, some of which are related to the next talk, actually. Thinking about a connection between how quantum algorithms simulate nature and how nature behaves, and see if at the intersection of them we can understand nature better, or we can produce natural systems that are of more use for quantum computing. Okay, here comes kind of the slide karaoke part of the presentation. First, on the topic of quantum advantage. So one of the areas we'd like to take on is asking whether post-quantum cryptography is as safe as everybody claims it to be. A lot of investment, both in terms of thought and soon in money also, will be made in adapting the world to quantum computing by developing post-quantum cryptography. And if it turns out that some of these post-quantum cryptographic protocols are themselves susceptible to being cracked by a quantum computer, we'd like to know that sooner rather than later. So here I'm pointing in particular to Umesh, who's sitting in front of me, who can explain this topic much better. But several folks in the CIQC, including him and Adam Booland, are kind of hot on this idea. Another area we're, as scientists, really excited about searching for quantum advantages is for the task of sensing. So there's this new concept that's been emerging that if you could connect a quantum sensor network to a quantum computer and do some kind of quantum computational sensing, you could measure things faster than you could otherwise. So the standard way of running quantum sensors is to measure, record, measure, record, measure, record, and then collect all those data, and then maybe look for an average or look for fluctuations. The concept with quantum sensing is a little bit different. You measure and then you store the state of the sensor. You measure, you store the state of the sensor. And with all these states stored, you now process that information in a quantum computer. And so one application that kind of pops out is, what if we can apply the idea of the Grover search algorithm to measurements obtained from a set of sensors and find a needle in a haystack faster? That kind of search task. You can think about a number of algorithms that would would come out of that would also justify the idea of like transduction, right? If you can coherently connect a sensor to a quantum computing technology, then you can implement this quantum computational sensing idea. Good, Brigida's here. Another direction we're really keen on pursuing is finally achieving, let's say within the next 6-ish years, quantum advantage for quantum chemistry of a real complex molecule. And the picture is, I guess Kevin was just telling me about this also similarly, that we're sort of at this stage where with the development of new algorithmic ideas, so for example, in the area of chemistry, one of the new things that we developed here in the CIQC is a different parameterization of the states of molecules that would allow actually the classical and quantum computation to proceed faster. But with algorithmic developments and really neat ideas about hallways and Minecraft layouts of quantum circuits, we can sort of keep chewing down the apparent resource requirements to carry out these kinds of calculations. At the same time, at the hands of the amazing quantum industrialists, quantum computers are just getting more and more capable. So those things are going to intersect, and those things we believe, if you kind of project out even not so optimistically, these things will kind of cross each other in the next number of years. Now, we within the CIQC are not operating these large-scale quantum computers that can solve the quantum chemistry problem, but we feel like we can both be chewing down the complexity of algorithms, but also providing more reliable resource estimations, so that will really draw in the interest from industry to carry out these calculations. That's our aim here. Okay, on the second topic, which is more sort of on the experimental end, there's a number of things that we're going to be pursuing. So one is operating like flagship neutral atom quantum processors. Dolev could probably describe this better than I could. So there's a number of ideas, and you can talk to him about the things that we feel like we can, even in a laboratory setting, like an academic laboratory setting, really play around with a variety of different architectures, of different error encodings, different ways of optimizing for certain types of expensive resources versus another. At the same time, we think we should look kind of far ahead and just think, where are kind of the fundamental issues with fidelity, speed, and scaling of these three quantum technologies? So let me highlight a few of those. In terms of fidelity, one of the things we're thinking about is whether different choices of atoms and ions would naturally allow you to operate gates with higher fidelity. And the current era of quantum error correction is such that if you can improve the physical fidelity, the physical qubit fidelity a little bit, right, that thing gets sort of multiplied by an exponential factor as you add more and more layers of error correction. So rather than say, hey, I made my physical qubit 5 times better, you've actually made your logical qubit maybe 125 times better because you've implemented several layers of error correction. So that makes us want to keep paying attention to how to improve fidelity of the physical qubits. And there's a few approaches we're taking. So for example, on the neutral atom side, one of the things we're curious about is whether different atoms than the alkali and the alkali earth metals would serve better roles for higher fidelity gates, for being able to detect errors through kind of erasures, for being able to constantly load while also holding on to quantum information. So here's one example, at least from my lab. We're learning to laser cool new atoms, but we hope to integrate them into quantum information science. On the ion side, there's a number of developments that we're keen on. One of them is to build sort of a more robust encoding into a single ion, which allows you to get sort of, if you will, one layer of error correction at the physical qubit level before having to add even more qubits. So our colleagues down at UCLA in particular have this idea of these AE codes, but basically it's something a little bit like the CAT codes that exist in superconducting resonators, but now making use of the multi-level structure of complex atoms, and doing that for ions. We're also looking at qubits like yttrium, where the quantum information that the yttrium ion holds is encoded in a nuclear spin without being reflected also in the electron spin. And that makes the qubit sort of immune to magnetic field noise. So we're actually in discussion already with folks at Quantinuum about developing this qubit and integrating it into their setup. On the superconducting side, we're pretty excited about learning better what are the underlying causes that for the superconducting qubit, the transmon qubits, to lose coherence in the time that they do. And we think that in particular we're learning how the phononic environment of these qubits impacts their coherence, and also how the phononic environment impacts also two-level systems, and the width of these two-level systems and how they could interact with superconducting qubits. So we feel like we can pay attention to the underlying engineering of these superconducting circuits without scaling up to the level that they do at Google and elsewhere. And if we can break through to the many millisecond level of T1 times in these qubits, then we can definitely imagine that that'll be very productively utilized by the large-scale quantum industry. In the area of speeding up quantum computing, we have a number of approaches. One of them relates to trapped ion quantum computing, and noting that the slowdown in trapped ion quantum computing is just the time it takes to move this very heavy object, a single atom, from one place to another on a chip, and how much faster that could be if we moved around much lighter objects. So let's replace the ion with just an electron, so 10,000 times lighter, and now this thing we should be able to shuttle around at much faster speed. So if you can imagine a quantum CCD architecture like they're developing at Quantinuum, but one where now just single electrons are floating around with the quantum information encoded in their spin, that would be a radical speed up for those technologies. So that's something that we're working on. We're also working on approaches to try to speed up neutral atom quantum computing. So one of the, as amazing as the neutral atom quantum computer is, one of its drawbacks, again, is that you have to transport atoms around quite often, to keep moving qubits on top of one another and to move things over to different zones in the architecture. And the transport of neutral atoms has been limited at a speed of something like a few meters per second. Turns out to be the speed limit for moving atoms around in optical tweezers. And we've been playing around with that idea a little bit at Berkeley, realizing that one of the methods that is used for moving atoms around also leads to a defect in the tweezer that drags the atom around. So if you rapidly scan one of these acousto-optical deflector devices, you make tweezers where at the focus the tweezer is very astigmatic and the trap is weakened. And that turns out to be the main reason why atoms are lost when they're translated from one place to another. But with an optical setup that accounts for that, we can not only get rid of that astigmatism, and that allows us to have tighter confinement even for rapid translation of atoms. That leads to maybe a three times speed up of how fast you can move atoms around. But also we can now control this lensing effect of acousto-optical deflectors, which allows us now to also translate tweezer arrays in 3 dimensions. And that could be useful for filling up a 3-dimensional quantum computing architecture. And then, let's see, more in the area of scaling, we're also looking at how to connect qubits at long distance. So I was just hearing about this active volume concept, that if you could put in some sparse connections at long distance, you could make even locally coordinated quantum computers actually gain a lot of capability in terms of the ability to conduct large-scale algorithms. So having long-distance interconnects between little quantum computing modules, even if they operate rarely, could end up being a really enabling feature for both neutral atom and trapped ion quantum computing. So we have some ideas for how placing quantum computers, Rydberg quantum computers, inside of optical resonators could allow for optical photon-mediated interactions between them, or also microwave-mediated interactions between Rydberg atoms. And that could allow for this kind of sparse, long-range connectivity in these kinds of quantum computers. In the area of trapped ions, the focus is going to be on building 3D ion trapping structures. So, we've seen the amazing work at Quantinuum where they, all of their thoughts are based on putting electrodes down on a two-dimensional plane and using them to control the electric field of the ions above. And because you're trying to influence an ion with just the handle on the surface, you're kind of limited. You can't necessarily build very, very tight traps. That ends up kind of slowing down how that quantum computer operates. But there's a new idea that folks at the CIQC have been developing, which is to use 3D printing to build electrode structures off of the chip, so you could build a ion trap cage around an ion. And if you could, with that also integrate some photonics in that three-dimensional structure, then at least as a single cell within this ion trap quantum computer, you have something where things can operate very fast. And then you could imagine, building that up as a CCD architecture and having an overall faster ion trap quantum computer. One last science idea I want to bring up is this idea of like a universal software stack. So this is relevant maybe to things you've been talking about, Craig, which is, so there's going to be fabulous advances that really have to do with superconducting circuits and 2 dimensions and the surface code. And then somebody else is going to work on some particular thing that works well for neutral atoms and something else that works for trapped ions. And certainly within each industry partner, they're going to work on their own thing. But how do we compare all the 3 of them so we can provide an outsider and also ourselves with like an honest evaluation of which setup, given which particular resource constraints and algorithmic targets, operates best. So that's something we hope to work on with our sort of computer architecture focus, is build a tool where for any particular task you can really take scientific data that tells you what is the capability of the system, apply it to different structures of a quantum computer, and then compare them to one another. Okay. Directing the CIQC is a Herculean task indeed, because we do a lot of other things than just doing research. We're also instructed to advance workforce development and education in this area. We now have, we're asked to go talk to the public and influence the public in terms of outreach. And then we also are asked to serve as a research coordinator, both obviously for the work inside the CIQC, but really provide some sort of leadership that helps coordinate what everybody is doing in this space. So there's a lot of activities that probably you'll receive emails about over the coming years. But for the purpose of this presentation, I wanted to highlight just 2 of them, which is our effort to develop a undergraduate quantum minor degree program, both at the University of California and also at the Cal State universities. And then also some advances in creating a discipline of quantum engineering and figuring out how to teach it. So I'll just give 2 examples that might interest our guests here. One of them in the area of the quantum engineering curriculum, a really exciting development the past year, and I got to thank Alp Sipaigil for his leadership here, is to offer a quantum engineering course to undergraduates and graduate students in electrical engineering. And what they're doing in this course is a quantum tape-out. So they're really learning the fundamentals of superconducting quantum circuits, sort of on paper, but then also now designing a real chip that should hold quantum circuits on it, qubits and control architecture, within which is compatible with tape-out. So the idea that you can basically just CAD up this chip and then send it off, and then while you're otherwise doing your homework, the chip comes back. And then you will also have the opportunity, the students in this course also have an opportunity to shove this thing in a fridge and test how it works. And this is something that even undergraduates, let's say here at Berkeley, but hopefully other places, would be able to experience in a class. So that's a really exciting development. We're using some of the seed funding of the CIQC to make this possible. And I think the students going through this kind of course are going to be just invaluable to the development of the fields. A second thing we're working on is a minor in quantum information science, which might feel like a minor contribution to the field. But I would say that that's not necessarily the case, because we feel that undergraduates in particular should probably continue to specialize in kind of the major topics that exist at universities. But they should be, that education should be complemented by enough to make them sort of quantum aware, enough that they, first of all, can go into, let's say, industry and be taught locally what they need to know about actually doing quantum computing work. That's something that probably locally at the industry setting is a better place to kind of let your, instruct your employees. But also to give them enough exposure to the field that they just get jazzed up about it. Like we want them to take courses where afterwards, when they're done with the class, they rush home, they call up their mom and they say, "You won't believe what I just got to do." And then that obviously will inspire people to come into the field. So that's the direction that we want to take with this minor that we hope to implement not just at the University of California, so let's say Berkeley and LA we're specifically working on, but also as a system-wide minor within the Cal State University system, which would then reach a huge number of people and really sort of fill the pipeline of people that want to come into this field. So we're working on that. One of the key parts of that curriculum will be like a project-based course where multidisciplinary teams of students come together and solve a problem. This kind of thing you see in capstone projects in engineering majors. It's pretty commonly done. And now we want to do it in the area of quantum information science. Okay, so that's what we're up to. And I'd love to team up with all of you, and I'd love to hear your input about what we're doing, and that's all I wanted to tell you.
Okay, we have time for maybe one or two questions for Dan.
Thank you for the really good talk. I was wondering, so one of the things I keep running across is that, in particular, recruiters aren't sure how to hire or find talent. How can we, is there any way that we could communicate with them as we're making these programs that these people have the skills that are needed?
That's a great idea. I think that's something, sorry, I don't have an answer. That's a great thing that we should do, is to talk to the people that are specifically recruiting. We have, like, again, on these panels, asked, and we've otherwise talked to a lot of people. I have an impression. The impression I have is that largely the quantum computing companies are looking for two types of people. One is they're looking for PhDs. Those are the most valuable employees in these companies. They want more and more and more PhDs that are coming out of the strong groups. And the only way we can address that is by gobbling more and more money from the taxpayer and producing ever more PhDs. So that's how that pipeline works. But what they also need is lots of other people. And what they need in those other people is like a mechanical engineer, an electrical engineer, a computer programmer. They need people who are solid in that base level of knowledge, people that do business development. And then in terms of whether the electrical engineer also is told something about decoherence and error codes, that's probably something I know that is the kind of instruction that can happen at the workplace. You can give people whatever, an afternoon session at Google Quantum AI, and they can learn what it is that they're building their electronic circuits for. So what we've been told, that's the input we've been getting, is let people focus on these core skills that we already are the center of our undergraduate and even a master's level education, but give them a little patina of quantum awareness so that they can at least get started in that new company, and moreover, that they get so excited that they want to work for these companies. But I think if we have more conversations with the recruiters, that would be quite helpful. Okay. Yeah, John.
I just had a question on the one slide at the end where students were designing superconducting circuits.
Yeah.
We're thinking something at Wisconsin the same way. Where do you make your chips? That's the hard part.
Let's ask Alp. I don't remember if it's happening locally or.
Students.
What's that?
It's one of his students who makes the chips.
Okay, looks like it's one of Alp's students that we're paying as a TA to do these things.
Yeah, and what's nice is if you kind of do it in-house, it's fast enough that they get feedback from the design to measurement quick enough. If you send it out to a commercial system, it could take months, and then it's not so engaging.
I see.
So,
But specifically given the kind of things you're asking the outside whatever fabricator to do. I mean, there are certain tape out processes that could happen very fast, but I guess what you're typically doing.
It's just a question of how fast and okay. But there's a lot of details there that are hard, but that makes sense. Yeah.
Okay. Yeah.
All right, I think let's thank Dan again.